All right, let's start off on number 1 here. So you can see that this is an exponential graph, or an exponential function here that we're going to graph. So we're going to start off with our points at 0, 1, and then 1 comma base. Now our base here is 5. And then I have a horizontal asymptote at y equals 0. And now I need to apply my transformations here. So I see in the exponent we have an x minus 1. So because x lies, I put that as x plus 1. And then for my y transformations, I need to take into account the 1/2 that's multiplying and then the plus 1 out back. So then we have 1/2 y plus 1. And so I'm just going to add 1 to my x values. And so that'll be turn that into 1 and turn that into 2. And I'm going to apply the 1/2 y plus 1 to my y values. So 1/2 plus 1 is like 1.5, 1.5. And then 1/2 times 5 is 2.5 plus 1 is 3.5, and then I do apply the y transformations to my horizontal asymptote as it is a y value, so that's going to turn it into 1. So I'll draw my asymptote there, and then 1 comma 1.5 would be right there, and then 2 comma 3.5 be right there, and so it looks like it's a growth right there, which makes sense because the base is 5. It's greater than 1, it should be growth. All right, next up here we have a log equation. So first we can answer the question of domain. So the domain of a log is always the inside of the log greater than 0. It does not matter what the base is. So I get here, when I solve that x is greater than 1. So that's going to go from 1 to infinity. And so next up I'll do my key points here. So for logs, it's actually the inverse of exponentials. So instead of 0 comma 1, it's going to be 1 comma 0. And then instead of 1 comma base, it's actually going to be base comma 1. So in this case, you can see our base is 1/2. And then our horizontal asymptote actually turns into a vertical asymptote at x equals 0 to start. Now I do need to apply my transformations here. So I have an x minus 1 inside the logs. That's going to affect x in the opposite way, you would think, because x lies. And then I have a plus 4 out back, which means we're going to do y plus 4. So I'm going to add 1 to my x values. And now that does include the vertical asymptote, which is now going to move to x equals 1, since that's an x value. And then I'll add 4 to my y values. So that'll be there, 2 comma 4, and then that's 1.5 comma 5. All right, so let's graph this asymptote here. And then 2 comma 4. 1.5 comma 5, so it looks like it's going to approach the asymptote going up and then kind of run away from it as it goes the other way. All right, next up here on number 6. So for this one, first we'll find the domain. We're going to take the inside of the log and set it greater than 0. So this one would be x is greater than 2, which if we wrote in interval notation would be 2 comma infinity. And then I start off with my key points here for logs, which are 1 comma 0 and base comma 1, just the inverse of the exponential ones. And then also the horizontal asymptote turns vertical at x equals 0. So my x transformation will be x plus 2. And then my y transformation is going to be a negative y out front because of that negative. It's outside the log, so it affects y. So I'll add 2 to my x's, and then make my y's negative. Now there's no such thing as negative 0, so I don't have to worry about that one. But this one should turn negative. My vertical asymptote will take the x transformation and be moved to 2. So I'll draw that one there. And my points will be at 3 comma 0, 5 comma negative 1. And then I'll just draw my graph here. It looks like it's approaching the asymptote going up. All right, next set here, we want to evaluate these logs here. So I always set these equal to x so that I can switch them into exponential form. So for this one, it's going to be 64 to the power of x. So the base becomes the base and it gets a new partner. And then what was with the 64 is now by itself. So you may not know what power turns 64 into 2. So if you don't know it off the top of your head, what I would say is what we should do is then just write this left-hand side as 2 to some power, and then leave that x outside. So let's see. That's 2 to the 4th power I know is 16, so 2 to the 5th would be 32, and that would make 2 to the 6th 64. So that's what we got here. It's the 6th power. And so once I have those bases the same, I can just set the exponents equal. So x must equal 1 over 6. All right, so same idea here. First, I'm going to set it equal to x. So we'll say 2 to the x equals. And then I always, whenever it's a decimal, I would always prefer that as a fraction just because it's easier to see. So I would write that as 1/4. And so then I can see that this would just be -2. The negative power drops it down to the bottom, and then the second power changes it into 4. And then lastly here for this one, well, actually, I already know that if it's a negative inside here, that's going to be undefined because we're not allowed to have negatives inside of a log. But if you actually switched it to 3 to the x equals -9, you could see that there's no exponent that turns a positive number negative. We know that 3 to the -2 power is actually 1/9. It's not -9. So this is impossible. That's why it's undefined. All right, next up here, we're going to set this one to equal to x as well. So we get 4 to the power of x equals 64. So then x has to be 3. All right, next up here, it says find the amount that the investment will have. So I'm going to invest $5,000. That means that's my P. And then this would mean my R is actually 0.0088 because as a percentage, you have to move that twice. And then compounding continuously means that I use the P times E to the RT formula rather than the other one. And then my time is going to be 7 years. So I'm just going to do this then as 5,000 times e to the power of 0.0088 times 7. I would type that in the calculator, and whatever I got would be the answer. All right, next one here is asking how much you should invest to end up with the following amounts. So this is actually telling me about A. And so this is compounded continuously, so I'm going to use A equals P times e to the RT again. So I'm going to plug in 10,000 right here, and then we don't know what P is, and then we do e to the power of 0.05 times 4. And then I would just divide both sides by that e to the 0.05 times 4. And whatever you get for that is going to be your p-value. All right, next up, these are asking us for domain, asymptote, and key points. So a key thing here for domain, first of all, we take the inside of the log, and this is a log, even though it's ln, that means it's a log natural, but the rule still applies here because for domain, the base doesn't really matter. I take the inside of the log and set it greater than 0. Now, since that +3 is not in parentheses, it is not inside the log. For adding or subtracting, parentheses has to be inside, or you need parentheses to show it's inside the log. So I'm just going to divide this by -1. I get x is less than 0, which is in interval notation -infinity to 0. My asymptote, or actually I'll do my asymptote and key points all together. So we kind of do this based on our process here of 1, 0, base, 1. So my base here is E, and I usually just estimate that at 2.7 for graphing. And we start off with a vertical asymptote at x equals 0. So then my transformations here, I just have a -x for that negative inside. And then for everything outside would be -y plus 3. So once again, that 3 is outside. So that's going to turn into -1, -2.7. And then the vertical asymptote does take the negative, but it's still 0. And then for my y values, I got to do -y plus 3. So this one's going to be 3. -1 plus 3 is 2. So that's the key info right there. All right, here we're switching to exponential. So I'm going to switch around my key points here. So I got 0, 1, 1, base, and my base here is E, so I'll use 2.7. And then for these, we're going to have a horizontal asymptote at y equals 0 since we are exponential. My transformations here, I have a -x, and then I have a 2y minus 3. So we can switch my x values to negatives there. And then my y values, I must apply the formula. So 2 times 1 minus 3 is -1. 2 times 2.7 will be 5.4 minus 3, which would be 2.4. And then my horizontal asymptote, 2 times 0 minus 3 would be y equals -3. So you can see that when we have a horizontal asymptote like this on our exponentials, it takes on the y transformations. Now for actually all exponential functions, domain is -infinity. You don't really need to think about it, so there you go. All right, next up here, I want to write this in this form. And whenever we have this form, the a value is the y-intercept if there's no shifts. So I can already know that my a value is 8. And I'm going to use my other point to kind of solve for b. So I know that I can plug in 1/8 for y, and then this is x. So, and I know a is 8 times b, which we don't know, to the power of 3. So I'm going to divide this side by 8. Now on this side I would multiply by 1 over 8, since that's the same thing as dividing by 8. So I got 1 over 64 equals b to the third. And then I would cube root both sides. And so the cube root of 1 is 1, and the cube root of 64 is 4. I don't need a plus or minus there because it's a cube root. We never do a plus or minus on a cube root. And furthermore, the base is always positive on these, so I don't need it kind of doubly. So I know a is 8, and then b is 1/4, and then to the power of x. All right, next up, we're evaluating this logarithm. So once again, I like to set these equal to x, and I'm going to say 125 to the power of x equals 1 over 5. So the base becomes a base, and it gets a new partner. So then this one may be a little tough for you. So what I would say is we should change this to 5 to the third to the x. And then this one, I would make this 5 to the negative 1. And so then I can write it as 3x equals negative 1. So x equals negative 1/3. Once I get those bases the same, we can just set the exponents equal. All right, next up here, number 28, same idea. So 64 to the x equals 32. This one's definitely tough. So I'm going to make this one 2 to the 6th power. I already figured that out earlier on the video. And then this one will be 2 to the 5th power. So then 6x equals 5. So x equals 5 over 6. All right, next up, same idea here. So 1/2 to the power of x equals 1 over 8. I can probably do this without change of base. I can just see x is 3 here, because if you think about 1/2 to the third power, it would just be 1 to the third over 2 to the third, which would definitely be 1 over 8. And it doesn't need to be negative, since that 2 is kind of already on the bottom. I don't need to move it to the bottom. All right, next up here, we need to find the domain in interval notation. So for any log, we have to take the inside of the log and set it greater than 0. So in this case, I'm going to have to factor. So I'm going to think of two numbers that multiply to -6 and add to -1. So that's -3 and 2. And I am going to need the box for this. So I have 6x squared. I got, let's see, -3x and 2x. And then I have -1. So this will be 3x plus 1 and 2x minus 1. All right, and so this is nonlinear, so inequality, I have to do a number line here. So I'm going to do -1/3, I'm going to do 1/2. If you don't want to do test points, you can always just think about what the graph would look like. So this is an upward facing parabola like so. So then these zones would be pluses, and those would be and that one would be minus. So we're going from -infinity to -1/3. And then from 1/2 to infinity. All right, once again here, we want to find the domain in interval notation. So it does not matter the base here. So the fact that this is ln does not matter for domain. We always take the inside of the log and go greater than 0. So I'm going to GCF an x here. And then I have to go back to that number line. So it'll be 0 and 1. And once again, we could just think of the graph here. Since this is a -x squared, it would be going like this. You could always do test points as well. And so this one's just going to be between 0 and 1. All right, next up, number 36 here. We actually have a combination of our two domain rules. We know that the inside of a log must be greater than 0. So I know that for that, x must be greater than -3. And then I know that the inside of a radical needs to be greater than or equal to 0. So if I solve that, it says -x is greater than or equal to -5. So x is less than or equal to 5 if I divide by -1, flipping the sign. So if x must be less than or equal to 5 and greater than 3, I would say that interval would be -3 to 5. We got a parentheses on the -3 and a bracket on the 5. All right, next up, we just want to rewrite this in exponential form. So whenever it's ln, that's really base e. So when I switch it to exponential form, it's going to be e to the power of, and then the new partner is y, and that means 200 is all by itself. Next up here, number 40, I'm going to switch this exponential. So the base, 13 is the base, the new partner is 2, and then 169 is all by itself. All right, next up here, switch this to log form. So on this one, we're going to switch it to a log of base 19. So the base of the exponent comes the base of the log, and then the new partner here will be m, so n is all by itself. And then this one, same idea. So base of our exponent is 7, so that'll be the base of our log. The new partner is 1/343, and then that's going to be equal to -3.